What about percentage composition? Now this one's a bit tricky as well. Now if you're finding any of these a bit difficult, or you think I'm going too fast, I probably am going too fast, but the point of this is that you need to practice the examples. Practice and practice over and over again. It's very difficult just to sit and listen to a lecture and be able to learn this on the first pass through, the first time you've seen this, okay? Percentage composition is analysed by mass or by combustion analysis. So if we've got a compound C6H8O4 and we burn that, we combust that, it's going to use some oxygen, it's going to oxidize, it's going to produce carbon dioxide and water if it's a complete combustion, so carbon dioxide and water. And we can determine that our C6H4O4, based on how much carbon dioxide we're producing and how much water we're producing, we can determine that this was 60% carbon, 4.48% hydrogen, and 35.3% oxygen. What is the percentage composition by mass of SO2? How do we work this out? Percentage composition by mass of SO2. So we need to say what percentage we have of sulfur and what percentage we have of oxygen overall in this molecule. So let's work out the overall mass of SO2, sulfur dioxide. 32 plus 2 times 16 gives us 64 grams per mole. That's the molar mass, 64 grams per mole. What percentage, though, of this mass comes from sulfur and what percentage comes from oxygen? Very easy to work out. 32 divided by 64 times 100, this is the percentage of sulfur, 50%. 32 divided by 64, this is the percentage of oxygen, gives us the other 50%. Super easy, super duper easy. Okay? In which of these compounds is nitrogen present in the highest percentage mass? Is it N2O or NO? Highest percentage by mass. Nitrogen weighs 14, oxygen weighs 16, okay? So 2 times 14 plus 16 overall is the molar mass of N2O, which is 44 grams per mole. Nitrogen weighs 14, we've got 2 of them, so it's going to be 28 divided by 44 times 100. That's going to give us our percentage, 63.64%. NO is nitrogen and oxygen, so 14 plus 16 is going to be the molar mass, 30 grams per mole. Okay, what about the percentage nitrogen? It's going to be 14 divided by 30 times 100 to give us our percentage, 46.7%. Higher percentage by mass in the N2O, isn't it? A higher percentage of nitrogen by mass. Here's a practice exercise. Morphine, derived from opium plants, has the potential for use and abuse. Its formula is C17H19NO3. What percent by mass is the carbon in this compound? Is it 12%, 54.8%, 67.9%, or is it 71.6%? C17H19NO3. Well, we're going to have to work out the molar mass first. Okay? Then we're going to have to divide our C17, so it's going to be 17 times 12 for carbon, divide that by our total molar mass. Let's work this out. So 17 times 12 plus 19 plus 14 plus 3 times 16 for oxygen. See, I'm rounding off these molar masses. You've probably noticed that as we've gone through. I've largely rounded off quite a lot. So we've got 17 times 12 plus 19 plus 14 plus 3 times 16 gives us 285 grams per mole. Now our C17 was 17 times 12, 204 divided by 285 grams per mole in total. That gives us 72, roughly 71.6%. So the answer is going to be D. I hope you're following along. For that one, there's the working out. Okay, you can see We've taken our amount of carbon, divided that by the molar mass of the entire molecule, and we've found it to be 71.6% carbon by mass. Here's another exercise. Consider separate 100-gram samples of each of the following: H2O, N2O, C3H6O2, and CO2. Rank them from highest to lowest percent oxygen by mass. I'll leave you work through this one. Okay, you can pause the video, work through it, see if you get the right answer. Here is the answer, ranked from highest to lowest: H2O, followed by CO2, followed by C3H6O2, followed by N2O, ranked in terms of percentage of oxygen by mass. It's not a surprise that H2O came first, because we know that hydrogen is relatively light compared to the oxygen. Now let's have a look at empirical formula calculations. So an empirical formula is a formula showing the lowest whole number ratio of elements in a compound. The empirical formula of hydrogen peroxide, H2O2, is HO, and butane is C2H5. So it's the lowest whole number ratio. C4H10 becomes C2H5. We can't get a lower ratio than that and have whole numbers. So for some compounds, the empirical formula and the molecular formula are the same. CO2, H2O, CH4, H2SO4. We can't get a lower whole number ratio for these ones. To determine the empirical formula of a compound, given the percentage composition by mass of each of the elements present, we need to divide the percentage composition by the atomic weight for each of the elements present, and divide each result by the smallest result obtained. Okay, so if you're given percentage composition results, how do you work out the empirical formula? It's really useful to be able to do this. So a compound containing sodium, sulfur, and oxygen has these elements present in the following percentages. So 29.1% sodium, 40.6% sulfur, and 30.3% oxygen. How do we convert this into the empirical formula? What we need to do is divide 29.1 by 23. Why are we dividing by 23? That's the atomic weight of sodium. So 40.6 gets divided by 32, the atomic weight of sulfur, and 30.3 gets divided by 16, the atomic weight of oxygen. Divide the percentages by the atomic weights. So we've got two 1.27s and one 1.89. We need to divide these numbers by 1.27. Now, the reason why we're doing this is to give us whole number ratios. Now, as it stands, they're currently already in a ratio. So we can say that we've got 1.27 parts of sodium, 1.27 parts of sulfur, 1.89 parts of oxygen. So 1.27 is to 1.27 is to 1.89, but we need whole numbers because it doesn't make sense. It's difficult to visualize without whole numbers. So if we divide by the lowest number that we get, which is 1.27, we can get 1 is to 1 is to something else. So it could be, let's divide by 1.27, 1 is to 1 is to 1.5. Now we don't have whole numbers yet. 1 is to 1 is to 1.5. If we double it, we will. 2 is to 2 is to 3. Okay, times 2. 2 is to 2 is to 3. So we're going to have Na2, S2, O3. Empirical formula, Na2, S2, O3. Not the molecular formula. Okay, we might have to double that or triple that to get the molecular formula, but that's the empirical formula.